Okay, so welcome. My name is András Kalapos. I'm a researcher, PhD student at the Telecommunication and Artificial Intelligence department at BME, and I'm going to present our rather confidently titled work with my PhD supervisor, Whitening consistently improves self-supervised learning. So the outline of my presentation is going to that first I'm going to cover some basics about self-supervised learning, and then I will present the motivation behind our work along with our primary contribution, and then that will follow some that will be followed with some basics of the mathematics behind our contribution, and then I will move on to our results along with some additional results in terms of analyzing feature space that is learned by the model that we train. Okay, so the very basics of self-supervised learning in vision, just to be on the same page. So the self-supervised learning methods that we build upon are in the so-called instance discrimination type of algorithms. So these work by, let's say, taking an image and then transforming this image to two different views of this image. These transformations are augmentations of common augmentations in vision, like blurring, cropping, and color distortions. And then the network is trained by embedding these views into a latent space or a feature space. And then the training objectives are formulated in a way that for views of the same image, these embeddings should be similar or close to each other, while views from different images should be different. And mainly the difference in these type of self-supervised learning methods are in the loss functions and mechanisms that implement this behavior, let's say in this box on the figure. So after pre-training an encoder in such a way, using self-supervision, the pre-trained encoders can be transferred to downstream tasks that are like classification or segmentation, any useful computer vision tasks in a classical transfer learning setup. So the motivation to our work is that one interesting but not heavily researched phenomena in self-supervised learning is the so-called dimensional collapse. So the loss functions and mechanisms in the self-supervised learning methods mainly work to avoid completely collapsed representations when the feature or embedding vector provided for different samples is the same or very close. So this is complete collapse. Most self-supervised learning methods or good self-supervised learning methods are good at avoiding that. Now, or in contrast, the dimensional collapse is essentially a phenomena when the embeddings produced by the encoder span only a smaller or not complete subspace of the feature space. This could appear as dimensions with minimal variation or minimal variability, or as correlated or just related dependent dimensions in the feature space. A couple of prior works presented whitening, in particularly zero-phase component analysis based whitening, to mitigate this issue. One particular work even suggested that this could improve accuracies for at least one algorithm, even if there is no visible collapse happening. Another motivation or another source of motivation to our work is that even the original batch norm paper, probably everybody in the audience or most heard about batch normalization. So even this original batch norm paper considers whitening as an option to normalize and also decorrelate the activations in a network. They discard it for computational and other reasons, but it is definitely an interesting topic to research, especially in self-supervised learning, for the decorrelation behavior and the avoidance of collapse patterns. So our primary contribution is to introduce this zero-phase component analysis-based whitening after the encoder of this whole self-supervised learning setup, sort of as a normalization, or we can view it as a normalization at the end of the encoder, or the output of the encoder. It's, I don't know if you can see the cursor, it is denoted by this curly W on all of our figures. So we train the network in this setup using self-supervision, and then also transfer this whitening stage to the downstream or any evaluation or downstream training part, along with, of course, the pre-trained encoder. So basically our hypothesis is that adding this whitening operation in this way in the self-supervised training could improve the quality of the learned representations and avoid collapse patterns. To test this hypothesis, we conduct experiments on multiple self-supervised learning algorithms and multiple data sets. And in addition, we also analyze the learned feature space along some metrics that we found from the literature. So let's discuss how this whitening operation works. Zero-phase component analysis is maybe familiar to some in the audience. If not, then principal component analysis, so PCA, is definitely familiar. So how this zero-phase component analysis-based whitening, so ZCA whitening for short, works is that first we center our features that are at the output of the encoder. Then we basically compute the PCA on this feature space, and then this by transforming with the principal components, we achieve to have unit variance in all singular vector eigenvector dimensions, and the only addition over PCA whitening in ZCA whitening is a final step where we transform the transformed features one more step back to the original basis of the feature space, but in a normalized and decorrelated way. So if we apply this to mini batches, this is very similar to batch normalization. That's why it is mentioned in the batch norm paper. But it not only normalizes the features, but also decorrelates them. And there is one more important detail that is to our work, is that to efficiently implement this operation in a parallel training setting, so on GPUs, we opted to use an iterative version of this method. It was published as called iterative normalization, which performs this whitening step, but based on Newton's iteration instead of computing PCA directly. So, moving on to our results. If you look at these learning curves, with or without whitening, we can notice that with whitening, which is the dashed curves, the accuracy scores are larger by a few %, and this generalizes to other small-scale data sets such as STL10 or Tiny ImageNet. And the blue purple curves are there only for reference, because that is self-supervised learning as a baseline. But for most of the self-supervised methods, we can see such an improvement that the solid curve is lower, or the dashed curve, which is the whitened solution, is somewhat better compared to the same method without whitening. If we plot this in a slightly different way, by plotting the improvement provided by whitening, then we can better support this hypothesis or our hypothesis. So in this figure, the positive values indicate cases, so data sets and algorithms when whitening does provide an improvement. And so the two most important metrics in self-supervised learning literature or research are, or the most common ones, linear probing and k-nearest neighbor probing. Both of these metrics show similar improvements, or at least no degradations, definitely no significant degradation in the performance. Finally, to analyze the feature space that is learned by the encoders in this setup, and to maybe uncover some avoided collapse patterns, we analyze the feature space by using very simple metrics mainly. Such metrics are simple statistical metrics from the literature, such as the variance or the correlation or covariance of the features, the rank of the feature matrix for a given and sufficiently large set of data points and embeddings. So we calculate these metrics by generating features for the validation data sets, and then assemble them to a feature matrix whose statistics can be easily computed. So most of these statistics are probably familiar to you, maybe except for the anisotropy, which is, or we refer to the ratio of the squared first singular value to the sum of singular values as this anisotropy matrix. High anisotropy matrix should result in a quickly decaying singular value spectrum that should correspond to a feature space that is not efficiently utilized, I would say, while lower anisotropy should be assigned for a better quality feature space. Now, these metrics are definitely good to highlight failure cases. So when representation collapse or dimensional collapse happens, they can indicate these issues. But however, they are not that good predictors for well-tuned, well-set-up self-supervised learning methods, but they definitely show a correlation with the accuracies to some degree. And as a final slide and conclusion, so we presented a method that uses this zero-phase component analysis-based whitening to improve self-supervised learning methods. We tested it on small-scale data sets, and probably the important takeaway message from this research is that we showed that such a simple traditional method like zero-phase component analysis or PCA can improve such a novel research direction as self-supervised learning in computer vision. So thank you for your attention, and if you have any questions, I'm happy to hear them.